Okay, so we have finished the 2 sections so far. In section 1, we just introduced some terminologies. And in section 2, we talk about the initial value problems. Initial value problem means a differential equation plus the initial conditions. You know, in order to determine the behavior, you know, of some real-world problems, you need some initial conditions like the motion of object. You know, you need initial position of the object and the initial velocity and those things. So that's called the initial value problem. So in this section 1.3, we're going to talk about some examples of applications of differential equations. You know, this is the course of applied differential equations. So a lot of real-world problems actually involve differential equations. And this is the major, you know, focus of our course. So let's just discuss those problems one by one. So we're going to talk about the population dynamics to start. So when we, you know, consider the population of a community, the population of the world, the population of the country, or the population of the state, we want to know how it changes with time. Okay. So the simplest model to describe the growth of population in a community for human beings or for animals, you know, we can always use some simplified models to describe the population change. So, you know, in the simplest case, we will assume that the rate of change of the population is proportional to the population itself. Okay. For example, if you have large population, then obviously the growth of the population will be more rapidly. You know, it gives more birth, basically. So that makes sense. So if P of T denotes the total population at time T, then dP over dt, which is the rate of change of the population, is proportional to the population at this time. So we can write down the population model as dP over dt equals some constant k times p itself. Okay, so that's population dynamics. This model turns out to be too simple. They only valid for the initial stage of the population growth. As the population grows, you know, you have to consider other factors involved. And then you have to add more terms in the equation. Okay, we're going to discuss those things in the second or third chapters. All right. So that's the first example. And then the next example is called the radioactive decay. So we have some elements, chemical elements that decay with time, like carbon-14. We use it to estimate the time of you know, the Earth age. You know, so how it works? It turns out the amount of the elements just decays with time, and the rate of decay is proportional to the amount of the substance. So again, we can write a similar equation. If we denote AT, the amount of substance remaining at time t, okay, then the rate of change of the amount of substance, dL over dt, will be proportional to the amount of the substance itself. Okay, so we can write down the equation dL over dt equals k times A, where k is again is another constant. But this time k is negative because when it decays, the amount of the substance becomes less. All right. So that's the radioactive decay. Okay, next example is called Newton's law of cooling or warming. When you put something out in winter, the temperature goes down. So the rate of the change of temperature of the object is proportional to the difference between the temperature of the object and the temperature of the environment. Okay. So the harder the object is, the faster it cools down. All right. So if T represents the temperature of a body at time T, and the Tm, the temperature of the surrounding medium, then the rate of change of the temperature of the object is proportional to the difference of the temperature of the object and the temperature in the environment. All right. So this works for cooling and also warming similarly. If you put something in a warmer environment, the temperature goes up, but the rate of change of temperature is also proportional to the difference between the object and the environment. Okay. So, you know, the larger the difference is, the more rapid the temperature changes for the object. So then we can write down a differential equation of the capital T over dt equals k times T minus Tm. Okay. So in the case of cooling, then k will be less than 0. Okay. In the case of warming, k will be greater than 0. Okay. It corresponds to cooling or warming. This constant k. All right. Any questions so far? Okay. The next thing is called the spread of disease. Okay, so like the COVID, or some other pandemic, when we describe this kind of social behavior, then we can use a differential equation to model this phenomenon. Okay. But the model becomes a little more complicated because the spread of disease occurs from the contacting of people, contact. All right. So you have to consider the people already contracted the COVID and the people who have not. And the rate of change of the people, with COVID will be proportional to the product of those two groups. Okay. So let X denote the number of people who have contracted the disease. All right. And Y of T denote the number of people who have not yet been exposed at time T. Okay, so we have two groups of people in the society, one group already contracted the disease and the other has not. Okay, then you want to know the rate of change of the number of contraction, how does the number of people contracted change with time? Okay. It turns out that we can write down dx over dt is equal to k times x times y, where k is a constant, a positive constant, because we are considering the spreading of the disease. So the number of people contracted with the disease will increase. Okay, K is positive. That means. But also, the rate of change of this number will be related to the number of people who have contracted and the number of people who have not contracted. So dx over dt is equal to k times x times y. So it's proportional to the product of the two populations. That means the more people you got contracted, then the rate of change will be larger. So if you have a lot of people contracting the disease in the society, then it is likely that the disease will spread more rapidly. Okay, but it's also proportional to the number uncontracted, because the contact becomes more. Okay, so that makes sense. All right, so let's just consider a small community which has a fixed population of n people. Okay, there's no flow in or flow out of the population. Okay, so that's a closed population. And then we can simplify the equation a little bit, or specify the equation a little bit. So if one infected person is introduced in this community, so that's the first person, not the first one, but there is one person contracted and enter into the society from outside. Okay, then x plus y, which is the total population in the society or community, will be n plus 1. Previously, we had n people in the community, but then one contracted person enters the society. So the total population becomes n plus 1. Right? Yeah. So then you can subtract x on both sides. You get y equal to n plus 1 minus x. And then you just replace y by this n plus 1 minus x in the differential equation. So you're going to get the dx over dt equals k times x times n plus 1 minus x. Okay. So that I can solve it. Now we only have one dependent variable x. We don't have any y. Then we can solve it. Okay. So that's another situation that we can use differential equations. Any questions about this model? Okay, so no question. Then let's talk about the chemical reactions. How many people took chemistry before? Okay, or are taking chemistry? Okay. So this is a kind of equation describing chemical reactions. Okay, suppose we have a simple reaction of two materials, A plus B. So they interact and form a compound C. All right, so that's a simple reaction that we consider in this model. So then we want to know, how fast the reaction rate is, how fast the amount of the compound C is formed. Okay. And turns out that we can also use differential equation to model this process. So if X denotes the amount of chemical C found at time T, all right. So that's for the compound formed. And if alpha and beta are in turn the amounts of the two chemicals A and B at time T equals 0. So initially, the amount of A is alpha and the amount of B is beta. All right, the components, Then the instantaneous amount of A and B not converted to chemical C or alpha minus X and the beta minus X, okay, because X is the amount of chemical, that's consumed. So initially you have alpha of A, but you consumed X. So what is remain is alpha minus X for A. Similarly, initially you have beta of B, but you consumed X. So what is remaining for B is beta minus X, okay? So then we can write down the differential equation like this. dx over dt, the rate of change of the compound formed is proportional to this product, alpha minus X and B minus X, okay? So this is what is remained for A and B. All right, so what it means is if you have more of any of the components, A or B, then the reaction rate will be more rapid, right? That's what it means in here. So dx over dt equals K times alpha minus X times beta X. We have another differential equation, and this K is positive, okay? All right, you get more and more of C. So that's the chemical reactions. Mixtures, this time it becomes a little more complicated, the mixtures, okay? So suppose we have a bank, and we suppose it has a constant volume of salt solution of 300 gallons. Okay, 300 gallons. So you have some input plan, input the flow and output flow for the bank. Then we want to know, the change of the concentration of this solution. All right. So let's just assume A denotes the amount of salt in the bank at time T. Okay, so that's the amount of pure salt in the bank at any time. It changes with time, okay, because of flow in and flow out. Okay. So suppose the output rate of brine is 3 gallons per minute. All right. Then what's the concentration of salt in outflow? The concentration of the outflow is the same as the concentration of the solution in the tank. It's flowing out from the tank. So the concentration of the outflow is the same as the concentration in the tank. So how do you calculate the concentration in the tank? You just divide the pure salt amount by the volume of the tank. So that's A over 300 pounds per gallon, isn't it? How do you calculate the concentration of a solution? You just divide the amount of pure substance by the volume of the solution, isn't it? That's A over 300. A is the amount of pure salt in the tank, and 300 is the volume of the solution, okay? And we also assume the input rate of brine is also 3 gallons per minute, okay, so that the volume of the solution in the tank keeps constant. Input 3 gallons per minute, output 3 gallons per minute, okay? And the input concentration of salt is 2 pounds per gallon, okay? So that's the input concentration. Then we can use those to calculate the rate of change of the salt. But we have to, distinguish between the input and the output rate. So the input rate of salt, that means the rate of pure salt input, okay? So that's denoted by Rin as equal to the concentration of the salt in the inflow times the input rate of brine. How fast is inputting into the bank? Concentration times the flow rate gives you the input pure rate of the salt. Okay, so the concentration of salt in inflow is 2 pounds per gallon given in the problem. Okay, you input some solution of salt with 2 pounds per gallon of concentration. Okay, from somewhere. And then the rate, input rate, flow rate is 3 gallons per minute. Okay, so you multiply these two, you're going to get 6 pounds per minute if you cancel the gallon units. You're going to get 2 times 3 is 6, and you get 6 pounds per minute. So that's the rate of input pure salt, 6 pounds per minute of pure salt, right? And then you can also do the similar thing for output of salt. So how much salt is flowing out, pure salt is flowing out per minute. Again, you have to multiply the concentration of the salt in the outflow with the flow out rate. Okay, concentration times the rate, how fast it's flowing out. The concentration tells how much pure salt is in the outflow. The flow rate tells you how fast it goes out. So again, if you multiply these two, then you're going to get the output rate of pure salt. Okay. The concentration of salt in outflow we already did. is AO 300 pounds per gallon. Remember? Okay. That's the concentration of salt in outflow. And the flow rate, output flow rate is also 3 gallons per minute. That's given in the problem. So you multiply these two. Again, the gallon and the gallon cancel. And you got 3 times AO 300. You cancel, 3. You leave up 100 in the denominator. And you still have A in the numerator. So that's A over 100 pounds per minute. So that tells you how much salt is flowing out per minute. How much pure salt. And then we can use those quantities to build this differential equation. So if you subtract the input pure salt rate and the output pure salt rate, okay, the difference will give you the change of the rate of pure salt in the tank, right? Okay, so change of the pure salt in the tank is because of the inflow and outflow. Okay, so you get dA over dt. That's the rate of change of the pure salt in the tank is equal to the pure salt inputting minus the pure salt outputting. So we already calculated those two, R in and R out. So just plug in, so we get 6 minus A over 100. So that's another differential equation. Modeling this process of mixtures. Okay, so it's actually not just mixtures, but also flowing dynamic process, right? Yeah.
Why did you not put A times the time in the differential equation?
8, which one?
You said like in the numerator, because
why don't we just write A over T? Yeah, that's just short notation. Usually, you don't have to write everything. A, we know that's the pure salt in the tank. It changes with time, so it's a function of time. But when you write down the differential equation, you can see on the left, we have dA over dt. That means A is a function of T itself. It indicates that. So you don't have to write it again on the right. Any other questions? Okay, let's see. I guess I'm going to stop here because it's already 11:45, and we don't have to finish everything in one class. So just leave a few minutes for questions, and then remember, we'll try to finish on Friday if we can, but remember we have a quiz, the first quiz on Friday. So if you have not bought the X code, please do it right away. The quiz will be from 11:40 to 11:50. All right. It covers the first 2 sections. Yeah.
So 10 minutes?
No, that's in online website. So that's why you need to buy the X code and get everything ready for the software. Any other questions? I guess I'm going to stop the recording. Yeah.
So the quiz will be up like 11 o'clock Friday?
No, 11:42. Okay, let me just.